Next up, we're going to be taking a look at the role of viscosity in two basic vortex flows. First off, we'll be starting with solid body rotation, and then we'll move on to an irrotational flow example. The goal in both of these is going to be to describe the lines of constant pressure so that we can take a look at the flow itself and get a better idea of how it looks. In solid body rotation, one of the key components of solid body rotation is that fluid elements do not deform. So in other words, our strain rate tensor right here is 0 because there's no deformation of the fluid components, which means that our stress tensor is significantly simplified down to just the components along the diagonal, because this is the Kronecker delta here. This corresponds to 0 when I does not equal j, so it leaves just the diagonal components behind, right? Now, because we're dealing with just the diagonal components, when we take our Cauchy's equation of motion and plug in this simplified stress tensor here, what we are left with is actually a simplification down to Euler's formula. So Cauchy's formula simplifies to Euler's formula. And when we take our velocity components, our radial and angular velocity, and we plug them into Euler's formula here, what we end up with are two partial differential equations. Even right here. So these two partial differential equations. Now, if we perform a separation of variables here, and we take the pressure component, and then we integrate, we can integrate and get an idea of what that pressure component will look like, right? So we take a partial integral here, and starting off first with this component, over here, we get this integral, where we take pressure with respect to r and z equals negative rho gz plus some unknown function g of r, right? And then when we take the partial integral of this component right here, we end up with so we perform a separation of variables, we take our partial integral, and we end up with pressure as a function of r and z is equal to density times gamma squared r squared over 8 plus some unknown function f of z. Now, when these two are consistent with one another, we wind up with this function right here, right? So you can see that this component goes here, and this component goes here. I'm going to erase this line in a second because it's ugly, but you can see that's where these components come from. And what this is saying is that your pressure with respect to r and z minus some p0 for when r equals 0 and z equals 0 is equal to rho gamma squared r squared over 8 minus rho gz. Now, if we take this function and we do some algebra to solve for z here, then what we end up with is what we were looking for in the start, our equation for the lines of constant pressure. And it looks something like this. And so what we wind up with are paraboloids of rotation. So basically these parabola-like lines here of constant pressure, right? And we get paraboloids because we have our second degree element in the numerator right here, right? So they're parabolic. And so that's what our lines of constant pressure look like in a solid body rotation situation. Now, we'll see that these look quite different in our irrotational flow, and that'll be in our next video.